If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Capital Isn't. Capital Isn't uses the latest economic thinking to zero in on the ways that capitalism is, and more often isn't, working today. Join Vanity Fair contributing editor Bethany McLean and distinguished professor of economics Luigi Zingales as they explain how capitalism can go wrong, and what we can do about it. Listen to Capital Isn't, part of the University of Chicago podcast network. How many dimensions are there in the universe? It seems like a simple question. I mean, you can pretty much just look around and count, and if you do that, you'll find 3 dimensions, maybe 4 if you're including time. But how sure are you that that's all there is? What if there are extra dimensions right in front of our eyes that we just haven't seen yet? This is the idea that we're going to talk about today. And we're not just pulling it out of science fiction. It turns out there are lots of reasons why physicists are looking towards extra dimensions to find answers to some of our biggest open questions. So today on our show, we're going to explore the world of extra dimensions. We'll talk about why people think they might exist, where they might be, and if these extra dimensions exist, could we ever access them? You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. Just to be clear, when we are talking about the word dimensions in this episode of Why This Universe, we don't mean other universes or worlds or something. We're not talking about parallel dimensions. That's not the sort of thing we mean when we mean dimensions. We literally mean that there's a direction you could travel in or something could travel in and through space that isn't north, south, east, west, or up, down. Like something else, an additional direction that you could travel through in space that for some reason we don't notice or perceive.
Right. Another way to think about it is like, how many lines can you draw that are completely perpendicular to each other, right? Like we can draw 3, but can you draw 4 or 26? 26 completely perpendicular lines. That's the question.
And maybe you can. I mean, I can't, but maybe a hyperdimensional being could one day. So there's a long history to these theories with extra dimensions. They go back at least to the late 19-teens. So this is just a few years after Einstein introduced general relativity. You know, all these notions that gravity is just the curvature of space, the idea that space and time are really wrapped up in part of the same overarching space-time, all these sorts of grand ideas. But Einstein wasn't done with that. That wasn't the end game for him. He wanted to build something that would be known as a unified theory, a theory that included all the stuff that general relativity does, all the stuff having to do with space and time and gravity, but also everything else we knew about the universe. In particular, he wanted to incorporate into this unified theory what we knew about electricity and magnetism.
We've done an episode on our show before about grand unified theories. In those theories, we are able to describe 3 of the fundamental forces together in one framework, but gravity is missing from that theory. A theory of everything would be able to combine that entire framework of grand unified theories with something also describing gravity. So with one theory, you'd be able to describe all of the fundamental forces in nature.
Yeah, I mean, so this challenge that Einstein and others took on in the late 19-teens is still an open challenge for physicists today. It's not surprising that Einstein failed at it, given how hard it's been for all the other physicists have tried for another 100 years. It's a really hard nut to crack. Probably the first real attempt to do this was this idea by a German mathematician and physicist named Theodor Kaluza, who wrote to Einstein describing his idea in a letter in 1919. A couple of years later, he published the idea, but first in this letter. And he proposed a version of general relativity, something very similar to Einstein's theory, but instead of 4 dimensions of space and time, so 3 plus 1 dimensions, he did it in 5 dimensions, 4 of space and 1 of time. So in general relativity, basically, the structure of the theory is set by these principles, the idea that the laws of physics are in the same in all frames of reference and things like this. So you really don't have any like free parameters to set. The theory just kind of comes out as it is. You don't have much choice to make. And that was true in Kaluza's 5D version as well.
So in other words, since all of general relativity is based on these few principles, like the fact that the speed of light is the same for all observers, that means that if we ever discovered that general relativity is actually wrong, then one of those fundamental principles must be wrong. This is in contrast to something like the standard model of particle physics, which has lots of different inputs that can be tweaked to match our results from experiments.
So it turns out when you take the original version of general relativity, the one in 4 dimensions, 3 plus 1 of time, there are 10 numbers built into the mathematics that kind of set the structure of the theory. And it turns out you need 10 numbers to describe gravity. So gravity comes out of this theory very well, but there's no room for anything else. When Kaluza extended this to 5 dimensions, this same mathematical object, instead of having 10 numbers, had 15. And that allowed to have enough room for gravity, along with 4 more numbers that you could use to describe electricity and magnetism. And then there was room for one extra component, we call a scalar field. But together, you could, in this 5D version, include things like gravity, electricity, magnetism, and a little bit extra stuff. So from this perspective, in Kaluza's 5D version of general relativity, there wasn't really a distinction between gravity and electricity and magnetism. They were all part of the same thing. You could think of the forces of electricity and magnetism as part of gravity. This was sometimes called the Kaluza miracle.
These 5 extra numbers that we got with this 5D version of general relativity, those just happen to describe something like E&M. It just is that convenient?
Yeah, that's the miraculous part.
So this is sounding pretty great. This is almost like magic. Kaluza extends Einstein's theory of gravity into 5 dimensions, and just like that, electromagnetism pops right out. So why isn't this our final answer?
Well, I mean, you've noticed there are only 3 dimensions of space, right?
I've noticed.
That's a pretty big problem, right? And there are other problems too. I mean, the original theory of Kaluza's, didn't know anything about quantum mechanics, which would be kind of unraveled in the years ahead. It has a lot of other shortcomings. But I would say that to a lot of physicists, Kaluza's idea was tantalizing, and it made them want to think more deeply about this and try to make this work. I mean, after all, they called it the Kaluza miracle for a reason. It was very tantalizing. All right, so a few years pass, and then in 1926, a Swedish theoretical physicist, Oscar Klein, kind of built on Kaluza's 5D theory, trying to make a quantum version of this theory. At this point, I need to mention one of the weirder aspects of Kaluza's theory that Klein incorporated, and that's that the extra dimension of space, that the one that we don't perceive, the extra one, is wrapped up kind of in a circle. So what I mean by that is if you were to travel along the 5th dimension, you would eventually wind up where you started. Kind of like circumnavigating the Earth by walking along the equator or something. But this is not a surface of something. This is the whole universe in this 5th dimension. Instead of going on in both directions forever, it wraps around on each other. So we call this a compactified dimension. So when Klein did this, Oscar Klein did this in 1926 in his quantum theory, he said, just like in Kaluza's theory, the 5th dimension is wrapped up like a circle. And it's a really small circle, maybe like 10 to the minus 32 meters or something. And this is why, according to Klein, we don't notice this dimension. So after all, in quantum mechanics, all objects, all particles, everything are waves. And in order for a wave to fit in a given volume in a sustainable way, it has to be small enough to fit in that space. So by analogy, if I have like a pipe organ or something, there's a kind of a longest wavelength that will fit in that, and therefore it can play only the notes down to a certain pitch. Lower pitch notes than that, a given pipe organ just won't be able to sound. So in the same way, this extra dimension could only hold particles with very small wavelengths, which means very high energies.
This key detail is kind of important here. In quantum mechanics, every single particle can also be described as a wave, and the wavelength that a particle has is determined by its energy. So more energetic particles have smaller wavelengths.
So to give you a comparison, a typical electron moving around an atom has a wavelength of like 10 to the minus 7 meters. And a proton being accelerated to the highest energies we can accelerate at the Large Hadron Collider has a wavelength of around 10 to the minus 17 meters. And in Kaluza-Klein theory, these dimensions are much smaller than this. Like I said before, something like 10 to the minus 32 meters. That is preposterously small and would require particles of incredibly high energy to propagate through or otherwise experience. We might be able to build a particle accelerator that could make particles go through that dimension someday, but not in my lifetime. We're talking about, trillions or even more times powerful than the Large Hadron Collider.
In order to test this kind of extra dimensional theory, we would have to build something like the Large Hadron Collider, but way bigger, that could accelerate particles so much that they have such a tiny wavelength that they would then disappear into this extra dimension.
Yeah. That's exactly right. And when you look at a particle that's zipping around this extra dimension, to us, it just looks like it's not moving. We don't notice it moving when it moves in the extra dimension. We just see it in XYZ space or up, down, left, right, forward, backward, or whatever. So an object moving very, very fast in a dimension we don't perceive the motion of, to us just looks like a stationary particle with a lot of energy. Or to put it another way, using equals mc squared, it looks like a very heavy particle or very massive particle that's not moving. We call that a Kaluza-Klein mode.
So if you've ever wondered what it would be like to see a particle from another dimension, here's your answer. Einstein's equation, E equals mc squared, tells us that energy and mass are interchangeable concepts, give or take a factor of the speed of light squared. So for example, a typical electron has part of its energy stored in its mass, and the rest of its energy is in its motion, what we call kinetic energy. But if that electron's motion was all going on in some dimension that we couldn't see, then all of the energy would have to look like just its mass. So an electron moving in an extra dimension would look to us like an unusually heavy electron staying still.
And think about it, if I take an electron and I put it so it has one wavelength around the extra dimension, then it will have a certain mass. And if I make it so it has two wavelengths, the next standing wave around that extra dimension, it will have twice that much mass, and then third 3 times and 4 times, 5 times. So in evenly spaced intervals, there should be new states, new Kaluza-Klein mode states of every kind of known particle, like electrons or photons or quarks or whatever, a tower of states. So the original Kaluza-Klein theory might have looked promising at the time, but it had some pretty serious problems and challenges. You could use the theory to calculate things like the charge and mass of the electron, but they didn't match any observations. Also, in the decades ahead, physicists discovered things like the strong nuclear force and the weak nuclear force and a bunch of different kinds of particles and things. And there just wasn't room in the theory. There were only these 15 components that just couldn't explain all this stuff. So no 5D version of general relativity, Kaluza-Klein or otherwise, had enough, content in it to explain everything that physicists discovered over the course of the 20th century. So, the theory kind of went away. I mean, some people worked on it. Einstein worked on it. There's a famous version of this theory called Bronsdicki theory, and those guys worked on it in the middle of the century. But not many people were really thinking about theories with extra dimensions for a long time until the 1980s. And the reason that it got popular again in the 1980s has everything to do with string theory. So this was around the time of what we call this first string revolution, when, and it was a huge deal in theoretical physics, but people started to think, a lot of smart people started to think that string theory would be the way that we would solve the problem of quantum gravity. We'd figure out how to unify the quantum world with the world of general relativity. And the problem, or maybe not problem, but a surprising facet of this is that to make string theory work as a theory of quantum gravity, the space-time couldn't just be four-dimensional. it had to have many more dimensions, like 10 or 26 total dimensions. And the rest of them were presumably compactified, curled up in tiny little circles, so we didn't notice them.
So if one extra curled up dimension wasn't enough for you to swallow, now we have even wilder options. The math of different string theories just requires that these very specific large numbers of curled up dimensions exist. Without all these extra dimensions, string theory wouldn't do its job of uniting the fundamental forces. But the problem is that doing an experiment to test for these tiny extra dimensions is impossible, at least for the imaginable future.
Just about the time I was starting graduate school in 1999, there became an explosion of new ideas about how extra dimensions might be incorporated into theories of the universe. These were different from the ideas that were coming from string theory, because in string theory, all these extra dimensions were so small that you could never do an experiment, or not never, but it would be very, very hard to ever do an experiment to test them. But these new ideas in the late 90s involved extra dimensions that were potentially observable, and that was very exciting. The first of these theories was published in 1998. It was written by three theoretical physicists, Nima Erkani-Hamed, Savas Dimopoulos, and Giacovalli. We call this theory the ADD theory for the first letters of their last names. And this theory involves relatively large extra dimensions of space. By large, I mean as large as maybe a millimeter in circumference. And to circumnavigate this dimension, you'd have to travel something like a millimeter. So in traditional Kluge-Klein theories, all of the kinds of particles can travel through all of the dimensions. Electrons or photons or whatever, assuming they have enough energy, they can move through the full dimensionality of space. But in this ADD theory, this theory with large extra dimensions, most of the particles, photons, electrons, protons, etc., are confined to live only in a subset of the volume, on something we call a brane. So you can think of it as a sheet extending through the dimensions of space. That sheet is the 3+1 dimensional universe that we know. Sure, there's extra dimensional space out there, but none of these particles can move through it, explaining why we don't see it very easily. But gravity can propagate through the full dimensionality of space-time in this theory. And that means that if you could do experiments about how strong the force of gravity is at the millimeter scale, find out how strongly things attract each other from gravity when separated by a millimeter or less, you could potentially test this kind of extra dimensional theory.
Because in that tabletop experiment, if you can very precisely test the strength of gravity, if it's like slightly not as strong as you expect, maybe it's going into other dimensions. Is that the idea?
That's right. Yeah. So as an analogy, imagine that I have like a candle, okay, and it's sort of emitting light in all directions. But now imagine that the laws of physics are such that the light from the candle can only go out in a plane. It can't go in all directions. It can just kind of go out in a flat plane. Then that candle will seem a lot brighter to somebody on the plane, because all of its light is kind of directed in that two-dimensional surface. In the same way, gravity might be a lot stronger than we perceive it to be, but most of it is leaking out of our brain into the extra dimensions of space. In fact, the original motivation for this ADD theory was to explain why gravity as a force is so much weaker than the other forces, something we call the hierarchy problem. So yeah, that's exactly the idea. We want to construct a theory where gravity is actually very strong, but is diluted because most of its influence is kind of traveling off into dimensions of space we don't experience. And physicists really heroically, build incredibly precise laboratory experiments to test the force of gravity with ultra high precision and ultra short distances. And sadly, I guess, inverse square law held up. So it appears that there aren't any millimeter sized extra dimensions, although, we can only put limits. So they could still be smaller dimensions of this kind, but none that were as big as the original paper was proposing. Also, people looked for this sort of extra dimension or evidence of this sort of extra dimension at experiments like the Large Hadron Collider. After all, you could maybe create Kluser-Klein excitations or Kluser-Klein modes of different kinds of particles, like gravitons, for example, in a machine like the Large Hadron Collider. And this would lead to observable signals, none of which have been forthcoming. So shortly after the ADD paper came out, a second idea, related but different, was proposed by Lisa Randall and Raman Sundram. So here, there's, again, one or more extra dimensions of space, but instead of those extra dimensions being large, they're very small, but very, very warped or curved. In other words, the geometry on this throughout this extra dimension is not remotely Euclidean. It's very, very curved, and that leads to some very bizarre sort of behavior. And again, there's the normal standard model particles. The normal particles like electrons, photons, and protons are all confined to what we call a brane. There are two different versions that they wrote about in two different papers. The first has two different branes separated by an extra dimension of finite size. So you have a brane with some extra dimensional space in between, and then another brane at the other end. And then there's a second version where the extra dimension goes on forever with just one brane on one side. Both have certain advantages and disadvantages. Again, like the ADD model, this was testable at the Large Hadron Collider, and we haven't seen any evidence of it yet.
I want to clarify with this very highly curved space, this is different than the kind of circular dimension that you were talking about before in the Kluser-Klein theory?
Yeah, that's a good question. So in the Kluser-Klein theory, even though that dimension wraps around on itself, it's actually flat or Euclidean. So this sounds weird, but this brings me to one of my favorite analogies in all of physics. So as a kid, I played a lot of the video game Asteroids. And that is the two dimensions of that screen are flat. You draw triangles on it and they add up to 180 degrees, etc. Parallel lines remain parallel, all that stuff. But it still wraps around on itself. If you fly your spaceship off the right side of the screen, you come around and just reappear on the left side of the screen, etc.
So like a Pac-Man screen.
Yeah, Pac-Man is also flat Euclidean. Yes, that's right.
So we haven't seen evidence for these string theories or these other extra dimensional theories at the LHC. Does that mean that we should think that they're not true?
Well, they certainly don't increase the odds that they're true. What they do tell us is, for example, in the case of the ADD model, that if there are extra dimensions, they're smaller than we had originally hoped they might be, maybe 10 or 100 times smaller, something like this. But they could still be there. And if we built a more powerful laboratory tabletop gravity experiment one day, we could explore, even smaller dimensions. If we build a more powerful particle accelerator one day, we could similarly explore smaller and more compact dimensions. But a lot of the enthusiasm for theories like this did subside when these experiments failed to detect evidence of them. All right, so I worked on the ADD and Randall-Sundrum models a little bit when I was a grad student in the years after that, but I worked on a different kind of extra-dimensional theory a lot more. This is a theory with dimensions that are kind of intermediate size, extra dimensions of intermediate size. So these are dimensions that are much smaller than an ADD, but still much larger than in the traditional Kluser-Klein theories. And unlike the ADD model, there's no confinement to a brane. All of the kinds of particles can travel through the full dimensionality of space if they had enough energy. We call these theories universal extra dimensions because they're universal to all the kinds of particles. And the reason that people like me were excited about them is because they seemed to offer a potential solution to the dark matter problem. So if I took a particle, like say a photon, and I gave it a lot of energy, like a tera electron volt, a TeV of energy or something, that's when we would expect this extra universal dimension to start becoming apparent. And then you could have a photon in a standing wave moving around this extra dimension. To us, what that would look like is something like a photon, but with like a TeV of mass. So really heavy, but stationary or slow-moving photon. This would be an object that doesn't have any electric charge. This would be an object that doesn't have any interactions through the strong force. and it'd be very heavy. It could have been produced in large numbers in the early universe. That sounds like a candidate for dark matter to me. And a lot of us were pretty excited about this. So we considered the possibility that there really isn't a distinct species of particle that makes up the dark matter. It's just normal particles that happen to be moving through an extra dimension of space. Now, like these other theories, we tried to test it. The Large Hadron Collider hasn't seen any evidence of this yet. The underground dark matter detectors haven't seen any evidence of this yet. And that certainly constrains this class of ideas, but there's still some space where it could be viable. And in the years ahead, I would say that it's likely we'll be able to kind of definitively explore this class of scenarios.
Would you ever work on these things again?
I mean, if there was a good reason. I stopped working on it mostly because I thought that all of the obvious things had been done. And and people were writing more and more papers that had like a new bell or whistle or some slightly more precise calculation. And I didn't care enough about this theory to want to do that.
Right. And I guess you're also you want experiment to be able to catch up to for it to get interesting again.
Yeah. Yeah. I mean, if I take a theory that I think there's a 1 in 10,000 chance of being true, I'll spend, a few months to construct that theory and sketch it, but I won't spend a few months to calculate some part of it to one more sig fig, and that's kind of where we got to in that. And I wasn't excited about doing more of that, but I wrote a lot of papers on it. So I don't want to get the impression that I jumped ship quickly. I was on the extra dimension train for a while. And if I'm being honest, I worked on it because I thought it was cool. I mean, it was just cool to spend my days thinking about extra dimensions of space. Who wouldn't like that?
Why This Universe is brought to you by the University of Chicago Podcast Network. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jay Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.